Hi, in this video we are going to talk about the applications of shortest path algorithms, so let's get started. Before talking about the concrete applications, let me tell a few words about a modified shortest path algorithm, the so-called DAG shortest path. Of course, DAG stands for Directed Acyclic Graph. So whenever we have a graph that has directed edges and devoid of any cycles, so there are no cycles in the given graph, then we can use this DAG shortest path algorithm, which is going to yield better running time complexity. So if the graph is a DAG, directed acyclic graph, so there is no directed cycles, it is easier to find the shortest path. We just have to sort the vertices into topological order. As you may recall, for topological sorting, we have to use depth-first search. So we iterate through the topological order, relaxing all edges from the actual vertex. So topological sort algorithm computes shortest paths in any edge-weighted directed acyclic graph in linear time complexity, so ordo E plus V. If you may recall, Dijkstra's algorithm has the running time ordo E plus V times log V. The Bellman-Ford algorithm is even slower. So basically, this DAG shortest path algorithm is very fast compared to Dijkstra or Bellman-Ford algorithm. And what's very important, then the edge weights can be negative as well. So the DAG shortest path algorithm can handle negative as well as positive edge weights. So whenever we have a directed acyclic graph with directed edges and without any cycles, it is definitely worth using DAG shortest path algorithm. And the application is, for example, solving knapsack problem, or lots of problems can be transformed into a directed acyclic graph where we have to find the shortest path. And in these situations, we can use the DAG shortest path algorithm. Okay. Of course, there are the standard applications of shortest path algorithms such as the GPS or vehicle routing or navigation, or as we have discussed with Bellman-Ford algorithm, that we can detect arbitrage situations in the forex market. But for example, we have the RIP, the Routing Information Protocol. This is a distributed algorithm that relies heavily on shortest path algorithms. Each node calculates the distances between itself and all other nodes and stores this information as a table. Each node sends its table to all adjacent nodes, and when a node receives distance tables from its neighbors, it calculates the shortest routes to all other nodes and updates its own table to reflect any changes. So the World Wide Web, I think it's pretty intuitive that the World Wide Web relies heavily on shortest path algorithm, because whenever we, for example, send an email or want to download something from a server or want to stream a video on YouTube or whatsoever, we have to acquire the data first. And of course, the optimal algorithm is to send the packages in the shortest path. And this is exactly what's happening in the background. So of course, the World Wide Web relies heavily on shortest path algorithms. Okay. One of my personal favorites is the so-called Evident-Shamir method. When we want to shrink an image, for example in the browser or on a smartphone without distortion, and we want to make sure the image will not deform, then we have to eliminate the least significant bit strings. And basically in these cases, shortest path algorithms can be very useful, although it is not that intuitive. So we set up a so-called energy function and remove the connected string of pixels containing the least energy. Photoshop and GIMP use it on daily basis. So it is a quite important approach. We build a huge graph. Vertices are the pixels and the edges are pointing from every vertex to its downward three neighbors. Basically like this. In this situation, the vertices are the pixels and the edges are going to point to the downward three neighbors. Okay, the leftmost and the rightmost pixels of course just have two neighbors. So the energy function determines what the edge weights will be. And it is an acyclic graph, so we can use topological order shortest path algorithm in order to find the string of pixels to be removed. I don't want to repeat myself over and over again, but why is it good to use DAG shortest path algorithm? Because it is much faster than Dijkstra or Bellman-Ford algorithm. Okay, another application of the shortest path algorithms is the longest path problem. Basically, this is the problem of finding a simple path of maximal length in a given graph. There is no polynomial time algorithm for solving this problem. This is the so-called NP-hard problem. It has a linear time solution for directed acyclic graphs on the other hand. So it is very, very common in computer science that if we want to solve a given problem, it would be very, very hard, NP-hard. But sometimes there's a linear solution. Whenever, for example, it is a directed acyclic graph, then in this case we are able to find the longest path problem, the longest path in linear time. Okay, and it has important applications in finding the critical paths in scheduling problems. Okay, we just have to negate edge weights and run the shortest path algorithm. I think that it is pretty intuitive too. If we would like to find the shortest path, we have to run Dijkstra's algorithm, Bellman-Ford algorithm, or the DAG shortest path algorithm. If we would like to find the longest path, of course we have to negate the edge weights. What does it mean? We have an edge, for example, with edge weight 10. If we negate it, it's going to be minus 10. So the edge weights will be negative, so we are not able to use Dijkstra algorithm. We have to use Bellman-Ford algorithm instead. And this is how we find the longest path. And the applications are parallel job scheduling problems. For example, given a set of jobs with durations and precedence constraints, schedule the jobs by finding a start time to each so as to achieve the minimum completion time while respecting the constraints. And as you may guess, these kinds of problems are very common in, for example, car manufacturing or, for example, hardware manufacturing. So we have lots of jobs, and of course there are some dependencies. And basically this is the CPM, the critical path method. That this method, by the way, was first used between 1940 and 1943 in the Manhattan Project during the Second World War. The problem formulation is that we want an algorithm for scheduling a set of project activities so that the total running time will be as minimal as possible. You may come to the conclusion that it is basically a form of longest path problem, and yeah, it is basically a form of longest path problem. So the algorithm needs a list of all activities required to complete the projects, the time or the durations that each activity will take to complete, and of course the dependencies between the activities. And with the help of this critical path method, which relies heavily on longest path method, which relies heavily on shortest path method, by the way, we are able to solve this problem. So that's why shortest path algorithms have several applications, and basically these are the most important ones. Thanks for watching.